Alright, we continue for part B of the problem that we started in the previous video. We want to show that a cannonball fired at 60 degrees and a cannonball fired at 30 degrees will travel the same horizontal distance, i.e. the range. Now, I happen to know in the previous video I showed how to calculate the time it took the cannonball to get there. Now that's not shown on this particular graph because this is X and Y, but if I had a YT graph, the time it takes to get to this point I showed was V0 sine theta over G. And because this is a symmetric problem, the time it takes to go up and the time it takes to go down would be the same. So 2 times that time will give me the time it takes to get down here where I calculate the range. I'm not going to take advantage of that. I mean, certainly if I was doing it and I was in a hurry, I would. But I want to show you how to work problems in general, not just special cases. So I'm just going to take the regular height type equation and I'm going to solve it for the particular problem for t for the time it takes to get to the final location. And then I'm going to take that time and plug it in to the x equation to calculate the range so that it can be worked in any problem, even non-symmetric cases. Of course, I want to simplify things if possible, and in this particular time that's 0 and this is 0. So I have now that 0 is V0 sine theta times t minus 1/2 gt squared. Now this equation can be solved since it doesn't have a constant term without using the quadratic formula. One just go ahead and factor out a time. So if I do that, I get V0 sine theta minus g over 2 times t times the factor t. And if either one of the two factors, either this term or that term is 0, then the equation is true. So one solution is t equals 0 seconds, and the other one is that gt over 2 is got to equal V0 sine theta, so that this term is 0. Now this one says that when the ball starts, it will be at y equals 0. Well, of course, when it starts, it's at y equals 0. I know that, but that's not what I want to know. I want to know the time it takes to get to here. So, while that's a true solution to the problem, it's not the one we're looking for. We need this time. So, let's solve for that time. If I do that, I get t is 2 V0 sine theta over g. Well, I said that V0 sine theta over g I had shown in the previous video was the time to the max height. So as we expect, this is 2 times the maximum height time. Notice this is not the maximum time. That's the maximum time. It's in the air. This is 2 times the time it goes to the max height. Now I want to take this time and now plug it into the x equation to calculate the range. So the range, which is equal to the value of x, is equal to x naught plus vx naught, which is v0 cosine theta, times the time. But I have a time now. It's 2 v0 sine theta over g. And I can simplify by knowing that that's 0. Now, this equation is fine as it is, but it has the complication that the cosine function, as you change the angle, that function changes, and the sine, as you change the angle, that function changes, and they don't change in the same way. So I like not to have two things changing. I like to have one thing change so I can make what-if type statements about an equation. Well, I happen to know something. 2 times the cosine times the sine, 2 cosine theta sine theta, is equal to simply the sine of 2 times the angle. So I can replace two things that are changing with a single thing that's changing. So my equation can be simplified to be V naught squared. Take the 2, the cosine and the sine, replace that with sine of 2 theta, over G. This equation shows up in many books. It's a special case formula. It shows up, for instance, in G. and Colley's 6th edition of physics that's used in high schools and in various trig-based physics courses. It shows up in lots of other textbooks, calculus-based, so forth. It's a special case formula. I don't know it off my head because it only works in special cases, but I can find it when I need it. Now, I want to use this now to look at the range for 60 degrees of an angle of firing and 30 degrees of firing. So I'm going to take a ratio just like I did in part A in that video. So R of 60 is V naught squared sine 2 times 60 is 120 over G. I'm going to divide that by the range for 30, which can be found as V naught squared sine 2 times 30 is 60 over G. Canceling things that are common, cancels the initial speed, cancels G. And we get that this is sine of 120 over the sine of 60. Notice that the speed of the cannonball, whether it was fired with a high velocity or a low velocity, doesn't matter. It doesn't matter whether it's done on the moon or on Jupiter or on planet Earth, assuming that we can neglect air friction. As long as there's some gravity so the ball will come down, the only thing that matters about the range of these cannonballs is the angle here in terms of whether or not they land at the same place. So a 60-degree cannonball, we're going to claim will land the same. Let's see how we do that. Well, we're going to put in what sine of 120 and sine of 60 are. Sine of 120 is the square root of 3 over 2. Sine of 60 is the square root of 3 over 2. So that means that that's 1. So the range of 60 is the range of a 30-degree cannonball. We proved that. Again, be able to work without numbers. That is the real power, and one of the main reasons people take physics classes is not to plug and chug. That's technician type level work. You know, somebody's already done it. They just tell you what to do, and you go plug and chug it. They pay less for that, and that can be replaced if I know exactly what they have to do. I can tell a computer to do it and eventually replace a human being. Being able to solve something from first principles, to solve something that hasn't been done, to play what-if games, that's a much harder thing. That is a better pain scale, and that's the sort of skills that doctors and lawyers and engineers and physicists and other professionals need to have if they're going to be successful. So practice that skill. Make sure that you get better. You only get better by practicing no matter who you are. That finishes this video for this particular problem.